Hello and welcome to the KSP Basics podcast. All right, so we're going to be going over some general background information about KSP since this is the first podcast that I'm making on this topic. So KSP is very similar to a KC value. It's just specifically applied to a salt that's generally considered partially soluble or insoluble. So this is not used for things like NaCl or KNO3 or the always soluble salts because they're obviously going to have high solubility. Therefore, they're not really going to be at equilibrium. Or if they are at equilibrium, they're going to be so product favored that it's really not going to be very important. This is very, very important, though, for the insoluble and the especially important for the partially soluble salts. This is going to let us know, even though generally they're going to precipitate out and form a solid, a little bit of the ions from these salts will go into solution. So you will have a small molarity of the cation and the anion, even when you have a completely insoluble, something that's going to be considered a precipitate, something that's not going to generally stay in solution. And because you have even just a tiny bit of those ions floating around, they can interact with other things that you add to the solution, or they can have an impact on the chemistry of whatever you're working with. So KSP just means the equilibrium of solubility or solubility equilibria. And this is going to basically be the overlap of solutions because we're going to be dealing with molarity values here and double replacement reactions. You will not always have a double replacement reaction, but this is frequently applied to double replacement reactions. So before we can get started on setting up or solving a KSP, we need to remember the solubility rules. And this goes back to Unit 3/4. So these are always considered soluble. So if you match anything up with sodium, it doesn't matter whether it's chloride, hydroxide, carbonate, it doesn't matter. It will stay dissolved in water. It will never precipitate out. These are never your precipitates, okay? Likewise, your anions, NO3- and the acetate ions. It does not matter what cation you put with them, they will stay dissolved in water. That's why we frequently use nitrate salts. Nitrate salts are great because they will go into solution. Now you have to remember from this list that even though all 6 of these, okay, always soluble, will always dissolve into water, they won't be the same as your neutral spectators. So, the ammonium and the acetate are not pH spectators. So they will dissolve into water, though they will be precipitate spectators. But these two here, they will change the pH of your solution. So you have to be really careful with those two because they're not on the same list and they can sometimes confuse you. So just be careful with that, okay? So even though they are changing the pH, they will be spectators in terms of solubility. Okay, so mostly insoluble, meaning these are going to be the ones. These here are going to be the ones that are frequently going to be your precipitate. The only way they won't be a precipitate is if they're with one of the always soluble ions, okay? So for example, silver nitrate is soluble in water because it's with one of the 100% soluble ones. But if you put silver with chloride, if you put silver with iodide, if you put it with sulfate, if you put it with hydroxide, it will be insoluble. Insoluble meaning not soluble, meaning it's going to be a precipitate. It's going to form a solid. That's what insoluble means, that it's going to be a solid. It's no longer going to be as ions in solution. Okay. Now, there are a lot of ions here that are not in this list. Calcium, magnesium. We frequently see these as precipitates. They have a much more complex set of rules. So they do precipitate with sulfate, but they don't precipitate with chloride or some version of that. And so they can be a little bit confusing. On the AP test, you are no longer required to memorize all of those minute rules. So those rules where they're very complicated. Most of the time, they'll tell you that two salts react and the precipitate forms. And just from the information here, you should be able to figure out which one is going to be your precipitate. So you don't need to memorize that whole long list. And technically, the AP test only requires you to know the always soluble ones here, but I would highly suggest familiarizing yourself with the mostly insoluble ones as well, because you're frequently going to see them as precipitates. So let's take a look at a reaction example. So here we have silver nitrate. This will be soluble because it's with nitrate. Nitrate's always soluble. NaCl. Okay, and remember, these are each in their own beaker. We'll be drawing a beaker diagram in a minute here. Okay, so you've got this solution and you've got this solution, both clear, colorless. Okay, and what we're going to do is we're going to take these two smaller beakers and dump them into a bigger beaker. So these contents both go into here. And the silver is going to react with the chlorine and the sodium and the nitrate, though we know they actually never form this. Okay, so my precipitate is going to be the AgCl, okay, because, whoa, a lot of things on the screen. The nitrate is always soluble. So if nitrate is always soluble, it can never be the precipitate. And we know that silver is frequently our precipitate. So when the two of these mix together, you're going to end up forming a white precipitate, which will at first be a suspension. So you'll see cloudiness, and then after a while, that'll settle to the bottom, and you'll just have solid sitting at the bottom, and the solution above it will kind of clear up. Okay, so that's your laboratory observations. All right, so we know that most of the time when we actually write this reaction, we are, before I draw the beaker diagrams, we're really going to just want the net ionic equation, because this actually doesn't form. We write it down in the reaction because we want to keep track of everything we have, and it is still in solution, but it's not really reacting because they're staying dissolved. So we're going to draw the beaker diagram, and we're going to write the net ionic equation for this reaction. So if we remember here, we've got the Ag plus and the NO3 minus. Here we have the Na plus Cl minus. Now when we mix these two together, I'm going to draw it at the bottom. You're going to have the solid once it settles down. Remember, at first it'll be a suspension. So you'll have AgCl at the bottom, and floating around in solution you'll have Na plus NO3 minus. And I didn't give you amounts, but whichever one is in excess for the Ag plus ions or the Cl minus, that would also still be left in solution. We'll pretend like it's a 1-to-1 ratio. By the way, when I wrote this reaction, the reason why I didn't have to balance anything or use any subscripts is because everything was a 1-to-1 ratio. Make sure you go back and review the ones that are not 1-to-1 ratios. So when I go to write my net ionic equation, because that's really important, the ion that's important from this beaker is the Ag+, because when I write the net ionic, I want to focus on what gives me the precipitate, because the formation of the precipitate is the whole part of this reaction, because that's what's actually changing. Otherwise, you're just mixing two solutions together. Chloride would be the component from this one, and then we've got our AgCl PPT. Okay, so this would be my reaction. This reaction is actually not what we're going to use for the KSP. That is what frequently confuses students. They think that the precipitate reaction is the KSP reaction, and then they get extremely confused. In order to set up the KSP reaction, what I suggest you do is you actually start with the precipitate. So let's forget about everything else that's in the solution. So we don't really care about the Na, we don't really care about the NO3. They're in there, but we're not really focused on them. Instead, we're going to focus on the precipitate that formed. So if we have AgCl, most of it is going to stay a solid. It's going to sink to the bottom and stay. But every salt, no matter how insoluble it is, has a teeny tiny bit. Again, even if it's your precipitate, it has a teeny tiny bit that will break into Ag+, which will be aqueous meaning dissolved in water, and Cl-. Okay? And the fact that these break up is going to be pretty important. So when we write the K value for this, okay, we always know that K is products of reactants, no different here. What makes it a KSP is that you're starting with a solid and it's breaking up into its ions. That's what KSP means. But how we set it up is going to be the same as how we set up any K. All right, so these are going to be based on molarity. So you're going to have Ag+, because that's product, times Cl-. Very important that you put the charges. Now this will actually be over 1, or you don't have to write it at all, because AgCl is a solid, and we know that solids are not included in a K value because pure solids are just 1. Okay, so there's a chart that you will get in your notes, or you have in your notes, that gives you a list of KSP values, and the KSP for AgCl is 1.6 times 10 to the negative 10. Well, what can we tell about this K value? This is going to be very reactant favored because it's a very small number. So for every billion or so AgCl solids, only 1 Ag+ will form and 1 Cl- will form. So that's very, very, very small amount of AgCl that will go into solution. All right, so let's actually try to solve a problem with this. Some important things to remember when you're solving with KSP values. So when you're just trying to solve for the molarity of the ions in solution, the volume of the solution does not matter. You will frequently get this to solve additional information, but you do not need this. The amount of solid does not matter as long as you have enough to actually dissolve that small amount, which is usually the case. So all you actually need to solve the problem is the KSP value. And a lot of times they'll give you more information because they want to ask you a part B, part C, part D, part E, and we'll try a few more of those in the next podcast. So I've just photocopied, well, I've written down, not photocopied, I've copied down our dissociation and our KSP, okay, and remember we got this from the table, and we're not including the solid in this, just the two ions, and I wrote out an ice chart. And so let's fill in the ice chart. So we know initially, if we have just AgCl solid, we have none of this. AgCl does not get included in the ice chart because it's not part of the equilibrium expression. And by the way, if it just asks you to write the equilibrium expression, this is all they want, is what's right there. So KSP equals this. All right, so we know that whatever we form of this, we're also going to form of the Cl. So we just have X and X. And so you'll just set this equal. So you'll say that the 1.6 times 10 to the negative 10 is equal to X times X. So that's X squared. And it's just a matter of taking the square root and plugging it into the calculator. Okay, so when you plug this in, you just basically take the square root of 1.6 times 10 to the negative 10. And you get X is equal to 1.26 times 10 to the negative 5. This will give you the molarity of the Ag+ and the Cl-. Since it's 1-to-1 ratio, they'll be the same. And so that would be your final answer.